Welcome to Study Loop.
We want to find the altitude above Earth's surface where the magnitude of the magnetic field is 50% of the surface value at the same altitude. So at a distance r from the center of the Earth, the magnitude of the magnetic field is given by B is equal to mu0 mu divided 4 pi r cubed square root of 1 plus 3 sine square of lambda m, where mu is the Earth dipole moment and lambda m is the magnetic latitude. The ratio of the field's magnitude for two different distances at the same latitude then will only depend on r, because this value here will be the same. So we have b2 divided by b1 is equal to r1 cubed divided by r2 cubed, with b1 being the value at the surface and b2 being half of b1. We set r1 equal to the radius of the Earth and r2 equals to the radius of the Earth plus some distance. So we have this equation becomes 1/2 radius of the Earth cubed divided by radius of the Earth plus h cubed. And we can solve for h to find the distance. So we have h is equal to 2 to 1/3 minus 1 RA. And this is 1.66 times 10 to the 3 kilometers. Now for part B, we want to know the maximum magnitude of the magnetic field at the core mantle boundary, that is 2,900 kilometers below Earth's surface. So for the maximum value, we said the maximum value is set lambda, sine of lambda m is equal to 1. And we have the radius is the radius of the Earth minus 2,900 kilometers. So it is 6370 minus 2,900. So this is the distance that we are, 3470 kilometers. And then we just need to plug in the equation. This becomes B max is mu0 mu divided by 4 pi r cubed square root of 4. And then this, when we use this value for the radius, is 3.83 times 10 to the minus 4 Tesla. Now for part C, we want to know the magnitude, and part D, the inclination of the magnetic field at the north geographic pole. So for part C, the angle between the magnetic axis and the rotational axis of the Earth is 11.5 degrees. So we have lambda m is equal to 90 minus 11.5. This is 78.5 degrees at the North Pole, geographic North Pole, so GMP. And the radius is the radius of the Earth, so we have B is equal to mu0 mu divided by 4 pi radius of the Earth cube square root of 1 plus 3 sine square of 78.5 degrees. And then this gives us a value of 6.11 times 10 to the minus 5 Tesla. Now for the inclination of the magnetic field at the north geographic pole, we have that this is the phi I is tangent of -1 of 2 times the tangent of the angle that we have there, 78.5 degrees, and then this is 84.2 degrees. So this is the inclination. And now for part E, we want to suggest why the values you calculated for C and D differ from the measured values. So for E, we want to know why the values that we got here for C, this magnetic field, and D are not the correct one. So a plausible explanation to the discrepancy between the calculated and the measured values of the Earth magnetic field is that the formulas that we use are based on dipole approximation, which do not accurately represent the Earth's actual magnetic field distribution on near its surface. So when we do this approximation and write this formula here, this is really good when r is large, but when we start getting close to the surface of the dipole, then this approximation becomes worse and worse. That's why there is a discrepancy, because we are trying to apply these values when we are really close to the dipole, to the source of the magnetic field of the Earth.